Here in example 2, we're going to be looking at a hydraulic piston cylinder system that's shown here in the figure. What we're going to be interested in here, contrary to the in-error problem statement that I have here, is what we want to do is relate the flow rate Q1 coming out of the valve to the piston velocity V, where I'm going to be defining the velocity as being positive to the left like this. And what we want to end up with is the transfer function. And from the transfer function, we'll get the input-output differential equation. We'll also do it by the block diagram approach to show how that's done and for you to decide which one is the easier approach for you. So let's start out here with our usual approach here of writing down the elemental laws first, the elemental laws that we're going to need are one if we look at the accumulator. And for the accumulator, we need to say that the flow into that accumulator, which I designated there by QC, is going to be equal to C times the time derivative of the pressure differential across that. So what I'm going to do is define a point C here at the bottom. So that's going to be PC minus the atmospheric pressure, the reference pressure, which I'll call PR. And PR is the same way over here. So this is going to be my equation 1. Now let's look at the piston. The piston is going to be going back to our days and looking at mechanical systems. So the first thing we need to do is draw an FBD. So if we put the piston and the mass load on here, I've got a force FC, which will be the pressure of the hydraulics acting there on the right hand side, and there's going to be a damping force, which is represented by B times V. So please also note that I changed the viscous damping coefficient up here from C up to B. The reason is I don't want to confuse the lowercase c for damping with the accumulator constant there of C. So please make that change. So with that FBD, and again recalling that I'm defining V as being positive to the left, so by using Newton's second law, well, first I'll say that this force FC, which I drew over there on the right hand side, that's the area of the piston A times the pressure differential. So that's PC minus PR. But my sign conventions here are, of course, that if PC is larger than PR, that means that the net force of the piston due to pressure is going to be to the left, as shown there in the figure. So this is going to be my equation 2. And now I use my Newton's second law when I sum forces acting on the piston. I have FC, I have minus BV, and that's equal to MA, which is MV dot. My continuity, if I look at node C, which I drew in my figure, the continuity is that the Q1, the flow in, that's the thing we're going to use for our input, is equal to the flow out, which is Q2 into the cylinder, and then the flow rate QC in terms of the accumulator. So this is equation 4, and I will also write down that the flow into the cylinder Q2, mass flow rate, is the area of the cylinder A times the velocity v. So as a piston moves to the left with some velocity v, it's bringing in a flow rate of a times v. So these are our 5 equations that we have. Now, in the last example, we dealt with things in terms of differential equations. As an alternative to that approach, and one which I usually find to be a lot easier to use, is I'll take a Laplace transform of all of our fundamental equations. The reason for doing this is that we get away from having to deal with differentiations and substitutions, and we reduce everything down to algebra. Okay. So what I'll do is the Laplace transform of equation 1, that gives me QC is equal to C times S times, and I'm going to shorthand this and just call this PCR. Then that gives the Laplace transform of PCR as that. So from this we see that PCR is equal to 1 over CS times the flow rate Laplace transformed into the accumulator. The Laplace transform of the force on the piston, that's just, again, the transform of equation 2 gives us A times Laplace transform of PCR. So that's my equation of 7. Laplace transform of the Newton's second law, that gives ms plus b times the Laplace transform of velocity, and that's equal to the Laplace transform of the force there of Fc. Laplace transform of our continuity equation, that gives Q1 is equal to Q2 plus QC. And finally, the Laplace transform of our equation 5 says that the Laplace transform of the flow into the cylinder, Q2, is equal to the area, cross-sectional area of the cylinder times the Laplace transform of the velocity. So again, the goal here on doing the Laplace transform here is that we don't have to deal with differentials. It's all algebra. What I'm going to do is take equation 6, equation 9, and equation 10. Those are the Laplace equations shown above. I get that Q1, therefore, is equal to Q2, which is AV, plus QC, which is CS times the Laplace transform of the pressure differential across the piston. I'm also going to explicitly use that equation down the road here in just a bit. And then this is equal to AV CS, where PCR we saw was equal to FC over A. So now from this equation, and again this is using equation 7, and so from this I see that the Laplace transform of the pressure force on the piston, Fc, is explicitly given by the difference between Q1 and AV times the ratio of the cross-sectional area divided by the accumulator constant C and the Laplace variable there of S. So now if I take that expression and put it back into my Newton equation, Laplace transform form, I get ms plus b times our output V is equal to Q1 minus AV times A over CS. So that's really all of our 5 transformed equations put together in one. I'm just going to reorganize things, rewrite this as C m S squared plus the damping coefficient, the viscous term B, accumulator constant there, C times S, plus A squared times the output variable there. V on the right side, our input, is A times Q1. So that's pretty much it. What I want to do is get the transfer function from that. Well, the transfer function at this point is just a matter of recalling that our output, in this case, is the velocity of the piston. The input is the flow rate there of Q1. So from that I get the ratio of the area A divided by CMS squared plus BCS plus A squared, like that. So this is our Laplace transform form here of our transfer function. If we want the input-output differential equation, I'll come up to there. I recognize that the S squared represents two differentiations with respect to time, so CM V double dot. I have a BC V dot plus A squared V. On the right hand side is A times our input here, the flow rate there of Q1 of T. So this is our input-output differential equation. So before we look at the block diagram approach, let's talk a little bit about the form of this equation. It's a second order equation. So it looks a lot like our mechanical system, strictly mechanical, or it looks like our LCR circuits that we've looked at. So what I'm going to do is put this in our standard form for recognizing things like natural frequencies and damping ratios. So I divide by the leading term of our differential equation, so I get V double dot plus B over M. The C's cancel out. I get A squared divided by CM V, and that's equal to the A divided by CM Q1 of T. So you might recall that this is what we call 2 zeta omega n. This is what is our natural frequency squared, and in our standard form this is oftentimes written as K times omega n squared. So from this we see that the damping ratio, the natural frequency omega n is the square root of A squared divided by CM. So that's our undamped natural frequency. Our damping ratio 2 zeta omega n, looking just at what we have above, is the damping coefficient divided by M. So from this we see that the damping ratio becomes B over 2 M omega n, and that ends up being B over 2A divided or multiplied by the square root of the accumulator constant there, C, divided by M. And lastly, we can say that the K omega n squared, the coefficient on the right hand side, is equal to A over Cm. So from this we see that the value of K is equal to 1 over A, and you might recall that we call that the static gain. The static gain being that, let's say we put a step input here of the flow rate of Q1. After all the transients die away, what's the steady state value of the flow, the velocity of the piston? That's just 1 over A times the amplitude of the flow rate of Q1. So all these have physical significance. Some things to observe here is that the natural frequency depends on stuff like the cross-sectional area A, the accumulator constant there C, and as you might be expecting here, the mass of the piston. Interesting, though, is that the damping ratio depends not only on the viscous damping and something to do with the scale, the size of the problem A, but it depends on the accumulator constant there of C. In fact, if we go back up to the original differential equation, we see that the effective mass here is C times M. The effective damping is B times C. So one thought here is, one question you may have is, why does one put an accumulator here? Well, you can see here that the accumulator here, in terms of the damping ratio, is effective in damping. If you find that your hydraulic system, your piston cylinder system here has oscillations that persist for too long, what you can do is add an accumulator, or if there is an accumulator there, increase the accumulator constant there of C. Go back to see the definition of C to see how that is done physically. But the accumulator here is effective in increasing both the damping and the mass, and in the end the ratios end up being that it goes as the square root of C in order to reduce the oscillations through an increase in the damping ratio of zeta. This static gain there of K sort of makes sense right away. In the static situation, the flow into the accumulator is a zero, and you simply see that if the steady state V is going to be equal to whatever amplitude that you have there for Q1, I'll call it Q1 naught, divided by A, like this, and that sort of makes sense. That the flow rate is just divided by A gives you the speed of the piston. So think about these things, because oftentimes in hydraulic systems it requires a little bit of extra thought to physically figure out what you've got. What I would like to do now, though, is use the block diagram approach to duplicate that same thing. Let's get a little bit of practice with that. What I'm going to do, in fact, let's do a quick look back at our equations. What I'm going to do, as usual, is I'm going to start out on the right hand side of the block diagram with an output, knowing that V is our output. So we're going to start here with equation 8. We see here that the output V has a transfer function of ms plus B times the force that's acting on the piston due to the hydraulic pressure. So if I do that block first, and I'll start there on the right hand side, is that here is my block. I have 1 over ms plus B. The output is the speed of the piston. The input is a pressure force there of Fc. So this is equation 8. That's what that block represents. Well, if you look back at equation 7, you see that the Laplace transform of that force is related back to that pressure differential there, PCR, through a constant there of A. So this is equation 7 above. And the pressure differential is related back to the difference between our input of Q1 and our flow, which we designated as Q2, the flow that goes into the cylinder. That difference multiplied by 1 over CS. So this is equation 11. And Q2, that comes about by looking at V multiplied by A, like that. Let me just do a quick look back to see what equation that was, because I forgot to write it down. So Q2 is AV, so that would be equation 10. So from this, we can see how our block diagram comes together just from our 5 basic equations. In this form, it's relatively easy to pull apart from where things come. This side here, that's our mechanical side. We developed that part of the block diagram from Newton's second law. The far left-hand side is the hydraulic contribution. And in between, we have our coupling. This is a coupling that exists between the mechanical and the hydraulic components. And then if we want to use this now in order to get our transfer function and our input-output equation, what we can do is recognize something we talked about before, is that when you have blocks like this in series, if I look at this block and this block and this block, recall that in series the blocks multiply together. So this is A divided by CS multiplied by the quantity MS plus B. So that output V with an input of the difference between Q1 and Q2 where Q2 is equal to A times the output there of V. Let me not have to write down this whole thing. Again, let me just call that block multiplier there of H. So from this block diagram, we see that V is equal to this transfer function, if you will, H of S, representing that block, times the difference between Q1 and Q2. From the feedback there, we see that Q2 is A times V. So this is H Q1 minus AV. From this, we solve for V, so this is equal to, we'll bring one term over on the left-hand side, is 1 plus AHV is equal to H times Q1. And therefore our transfer function becomes the open loop transfer function H divided by 1 plus AH. And if you multiply this out, you'll find that that's the same transfer function that we got above if we didn't use the block diagram approach. So again, on this problem, we took two approaches to get to the transfer function. One was the more basic route, I think, was that we began with our elemental equations, which are obviously time domain equations, 1 through 5. We did a Laplace transform of those, recognizing that dealing with algebraic equations is a lot easier than differential. And then we combine our Laplace transform equations, as we did here, to get our transfer function as that. And by looking at the block diagram approach, we put the blocks together, working from the right to the left, starting with the output and moving back toward the input. We got that. Through block diagram reduction techniques, we combined those three blocks into one block H and worked as that.